Be here. Great to be present at CogX 2018, and great honor to do a presentation in the Turing research session. Alan Turing has done a lot of things, as we have seen earlier, and he also coined the phrase, the term, thinking machines. And I think he thought about something quite different from what I have in my mind, or what he could have thought about, but in a way it fits to soft robotics. So first question to the audience, have you heard of soft robotics, soft robots? Anyone, you have heard of it? Yeah, some nod, okay. Do you know what a soft robot is? Those who have heard about it? Some idea maybe. I also had quite some idea on what soft robots are, but then had to find out that there are actually all kinds of soft robots. And so I would like to show a few. So this is Sami Haddadin, who is now a professor in Hannover. And he wants his robots to hit him very hard, as we can see here. And as you can see, this is a very sturdy robot, made of rigid components. But he sees it as a soft robot because he uses sensors to detect the interaction with his head and the robot, and then controls the robot to behave in a compliant and soft way. Other examples are coming now. So another approach was to introduce something called the series elastic actuator, was invented 20 years ago by Gil Pratt. And the idea is there to put a spring in series to a motor inside a robot device. And so the Baxter robot can now come out of the cage and can be used in a factory environment very close to humans. And we can see the robot now operating there, and as you can see, also in the vicinity of humans. So even though, again, a very rigid device, it is considered soft and compliant because of its actuation mechanism. Another example for a soft hand is the IIT Pisa hand by Antonio Bicchi, and we have very long discussions about what is actually a soft robot. And again, you can see quite a few rigid components in there. But the clever bit is in the actuation mechanism, which is a soft band, a soft rubber band that makes it overall very soft. Anyway, I think it's good to be inclusive, and different people have different views on what soft robotics are about. My view is really soft hardware. So that's what I'm working on. And I would like to show this one here. That's what I usually show. The octopus is an amazing animal and gives a lot of inspiration. So as you can see, it is squeezing through this very narrow opening there because no bones inside the body. So extremely soft. But the interesting bit is it can control its softness. So it can vary from soft to stiff. So the octopus can squeeze through narrow openings, but can also catch prey, walk on the seabed, etc. So great source of inspiration there. So here's another example. We see the tongue of the chameleon doing an incredible feast here. And maybe it doesn't solve all the problems in soft robotics, but one thing is for sure in my mind, we cannot use the standard rigid component robots to solve these kind of tasks. So taking this inspiration, a number of researchers have worked all over the world to create now robotic devices that take this inspiration from the octopus, for example, and other soft animals to create robotic devices. And you can see here some of the examples from Harvard and also from Pisa, made of silicone rubber and inflated by air that can move around. And I want to highlight the one. Soft Robotics is actually a company selling now a commercial product based on soft robotics. And you see this gripper is capable of grasping a wide range of objects without any problem. Now let me step back a bit. A few years back, we had a project on soft robotics, and the idea was to take these soft robotics principles and create surgical tools. So this was a STIFF-FLOP project, and we can see here now a standard robot arm robotic system that is used for surgery, the Vinci surgical system, very successful. And you can see here now the standard robot system used there, so very rigid components being used and then let loose on the patient for keyhole surgery. So we wanted to really move away from this standard type of robot that we know from the car manufacturing industry. They have their job, they have their place, they can be very accurate, very fast, but also very strong. But we would like to take the inspiration from the octopus and create something that is more like this and see how that can be applied to problems like a human-robot interaction, as it is the case for keyhole surgery. So from the outset of our project, we wanted to really draw a line and develop these very soft systems. And you can see here an artist's impression of a modular robot made up of a number of modules, each individually controllable. And I'm moving forward very quickly now here, really skipping over years of a lot of research to show what these robots look like that we have developed. So we can see in gray the silicone rubber we have used, and then in black these are the chambers that can be filled with air to actually move the robot around. And putting these together, so here you see two segments now attached to each other and individually controllable, we can actually create a robotic device that can move in space. And we found it can actually operate at quite high speed, and it can also do that in a very robust way. And I should really mention this is real time here. We haven't speeded up the video at all. I should add that we are not necessarily interested in carrying out these kind of movements inside the human body, but it shows what they are capable of, these kind of soft robots. Anyway, so we moved forward then and created devices like these. So this was our miniaturized prototype, equipped with a camera at the tip, again made up of two individual segments which could be individually controlled, and they were small enough then to actually move through a very narrow opening, a so-called trocar port, inside the human body. And so you see here a phantom where we are moving into, and the camera images show show what's the camera seeing while we are moving ahead. So very dexterous system, and we were also able to do a first in human in the context of minimally invasive surgery. So it was the first time we had a soft robot moving inside a human doing minimally invasive surgery, and under the guidance of medical doctors, surgeons, we could show that it worked, and we had a more an improved way of observing the inside of the body. No worries, I'm not showing you the inside of the body in this kind of presentation. And I should also highlight this was a dead person. No one was killed as part of the project. I should add that. Anyway, so we were very good in creating soft robots, but something that was missing was to have something that could also change its stiffness. So a bit like the octopus, which is capable of being soft at one point, but also then changing to a stiffer kind of state. So we developed something we call the Antagonistic Inflatable Robot. And this robot is made of fabric. So it's an outer fabric shell, and that is airtight and can be filled with air. So we can create a structure through inflation. But in addition, we have tendons attached on the outside that allow us to move this inflated structure around in different directions. The interesting thing here is that we can now move it about with those tendons, but by controlling the pressure and the tension on the tendons, we can also change the stiffness. So we have an antagonistic actuation mechanism that allows us to navigate and change stiffness. And so we have tried this out, and it can move around in crazy ways. And I think here are some videos just to illustrate that. So we could also inflate it from a very small volume to a large extended volume to go into inaccessible spaces. Once you have done your job, you can deflate it again and take it out as shown here. And obviously, once you are in your space, you can move it around using the tendons as shown here. And it has already a kind of very lifelike kind of movement, very similar to the octopus, I have the feeling. So very natural movement here. And obviously, being interested in the surgical aspect, we tried that also through these trocar ports, going into an abdominal area or a phantom here, inflating the robot, and then moving about. Very, very primitive yet, but the concept is there, and I think there is lots of potential. We like this idea of stiffness controllability so much that we also applied it to robot arms, so like the one shown here on the right-hand side. So a very standard robot arm with a number of joints and links that can move about. There was a lot of work on the SEA, the Series Elastic Actuator, which I have shown already earlier. And the focus was really on attaching springs and complicated mechanisms to the joints of these robotic arms to make them more compliant. And we thought, okay, all the focus is on the joints. Why can't we do something with the link of these robot arms? So we introduced the variable stiffness link, or VSL, and here it is in all its glory. And the main idea behind it is to make this link be capable of changing stiffness. So here you see now one of these robot arms that we have created, and the special bit is in the links. And as you can see now they're very stiff, so the robot arm could be used to carry load and move about, carry out certain tasks. But then if we let the air out, we reduce the stiffness, and the robot arm becomes soft, becomes compliant, and can be more safe in the vicinity of humans, as demonstrated here. So a very cheap way forward to turn a robotic device into a safe robot that can be used in human-robot interaction. Good. So I hopefully gave you some flavor of the work we have been doing, and would like to look at some advantages and challenges in that area. So there are quite a number of advantages, and that is probably not a complete list here, but definitely one can see it's more dexterous, has a more natural movement, a robot arm like this. It adapts to the environment very nicely. We see an increased application range, so it can be used for human-robot interaction, for example, and linked to it, we have increased safety. There are quite a number of challenges. They can adapt to the environment, but sometimes you want to do something that is not easily done with a robot arm that is so difficult to model and to control. So, for example, position control is really an issue. The payload is very low. With a soft arm, usually cannot lift a lot. And miniaturization is also something we are still working on. So myself, I'm very interested in this idea of stiffness controllability, as you might have seen. So what I would like to create are robots that can combine the best of two worlds. So on the one hand can be strong and stiff, and on the other hand can be compliant and soft. So a bit like the octopus. Now when I think about soft robotics and artificial intelligence, two things come to my mind. So one is a term called morphological computation. And the idea is here to argue that not all the intelligence sits in the brain, but that the body also can be intelligent. And we can see that in nature, animals can adapt to the environment. They have special arms and limbs that are adapted for the particular environment they are in. And I will show some examples in a minute. And I want to come back also to what I said about thinking machines and Alan Turing. Maybe he was really ahead of his time, because in a way it's not saying thinking brain, but thinking machine. So it's incorporating not only the computer that sits there, but the whole mechanical structure that can have a certain intelligence. The other thing I would like to talk about is deep learning, deep neural networks. You might have heard of them. And they can be also used for soft robots. So these are structures, computer programs if you want, that are very complex. In a way, I'm contradicting myself now, because on the one hand I'm saying, okay, we have morphological computing, we want to reduce the computational burden, we want to reduce the brain power that we need to move robots about. But maybe we are not quite there yet, because there are a number of robots and it's very difficult for us still to control them. So for example, to do position control. And so here, this deep learning or these learning mechanisms, machine learning comes to play and help us to train these robots. And possibly also in the future to help us to design better robots. So I have a few more examples which I would like to show. I'm not aware of the time. But if anyone can tell me how much more I have. No? Okay, good. A few more minutes, then let's go through this. And I have another question for the audience. So how many sensors do you think are in those robots? Maybe one sensor? One colleague already knows. Then maybe I ask another question. How many microcontrollers do you think are in there? A big microcontroller, a simple one? Any feel for it? Well, you know already about these robots, I suppose. So the answer is correct, 0. Yeah? There's no sensor in there, no microcontroller. So it's just a simple vibrational motor that sits in there and makes these little tentacles move about. And so they move in this environment. They effectively bounce off the wall. And the interaction with the environment gives us the feeling they're doing something purposeful. I want to show also this example here. So this is actually a dead fish, according to the researchers from the University of Florida, and it's just lying in the water. And the moment they switch on the water stream, the fish actually starts swimming. So they argue that the water stream is actually used by or the energy in the water stream is harvested by the fish and turned into these kind of movements. Another example are these goats, which I think are very funny. And they're just standing there, climbing on the trees, standing on them in a very relaxed way. And so one might argue, yes, there is not a lot of brain power needed to make them actually do this task and stand there. So something in the hooves maybe that is very clever to allow these kind of tasks. Another example is the ibex, and this one in particular is now climbing a dam wall. And it seems to be fairly comfortable in doing so. And I just moved to the last sequence of that, and you can see them sitting there in the wall, very, very high up. So it's a serious matter. So one of my colleagues now at Imperial College, Srishanta Nanayakara, he's actually taking this now to the next level and wants to create robotic hooves. And he has already shown with his work that by modeling that and copying what he could learn from the natural, the animal hoof, he could create a system that reduces slip. Another example I want to bring is the inherent sensing capability that we have in our viral stiffness link. And as you can see here, or I try to explain. So we have a pressure system, and we need the pressure to keep our system going. So we can now look at the pressure and use it effectively as a distributed sensor. So wherever there is now an interaction with the environment, a collision, we can sense that and can use it to retract and change the stiffness, lower the stiffness. So now one example on using machine learning to actually help soft robots to do something meaningful. So this is work by Bielefeld. You see the robot doesn't really know what to do. Yeah? So the instructor is holding up some item and the robot is supposed to move there. But it has no understanding on how to link the position of the ball in space to the pressure that is needed in the actuators to move there. So through neural network training, machine learning training, the robot can actually, with time, learn to do that. And so effectively, the robot is moved through all kind of possible combinations of movements, and that can be done in software, or as shown here, with a real robot. And after a while, the system has learned now to actually understand where this is, this item, and follow it. I come to the end now. A quick acknowledgement, especially to the students and research assistants that have been working with me and to achieve all these various things. And finally, I would like to show you our soft robotic hand that we want to use in prosthetics. And that brings me to the end of my presentation. Thank you very much.